Hello, a few videos ago we set out to do one loop calculations in QED, right? And we found three loops we needed to calculate, right? The one loop correction to the photon propagator, the one loop correction to the electron propagator, and the one loop correction to the QED vertex, right? We already did the first two, and today we tackle the last one, which is this diagram right here, right? We know that this guy contributes to this 3-point function, right, which is the vertex function of QED, which at leading order is just this guy, but now we have the loop and the counter term, right? We call this guy minus I E gamma mu, right? And the counter term for this guy is just minus I E gamma mu delta 1. Right? And we have shown a few videos ago that gamma mu can be, in general, due to word identities and the general structure, Lorentz structure of this function, can be written in terms of the form factors f1 and f2, which is proportional to this Lorentz structure right here. This is F2, right? Where Q is the momentum of the photon going into that vertex, and this is the mass of the electron. Remember, this was proven with, and we had in mind a situation where this the electron is on shell. Both these lines are on shell, and this describes the interaction of this one shell electron with the rest of a more complicated diagram, right? So in general, that can be written for that vertex, right? And now, as far as renormalization goes, right, we probably didn't even need to calculate this guy, right? You might remember that we have, in the same video, we have shown this. We have also proven that as a consequence of the Ward-Takahashi identities, that delta 1 is equal to delta 2, right? These being equivalent to this, right? Z1 is equal to Z2, right? Where Z2 is the correction to the electron propagator, and Z1 is the vertex, intrinsic correction of the vertex, right? Since we already renormalize the electron propagator, right? We calculated the electron self-energy. We already know delta 2, so we know delta 1, and that's the beauty of symmetries, right? It allows us to save time. But this loop also has a finite correction, a finite part, which has very important physical consequences, right? And it also has infrared divergences, which we want to treat, right, still. And we'll do that on the next video. But in order to see that those infrared divergences, we really need to calculate this loop, right? That will also allow us to check if this is really true at one loop, just to see if we're reinforce our trust in the Ward-Takahashi identities. But the main reason we want to calculate this in this video is to really take a look at the finite part and have a expression for this guy that we will later use to look at the infrared divergences, right, on the next video. So let's write the Feynman rules for this guy. Let me put it here. And now write an expression. Let me define the momenta here. I'll call the momenta going through. I'll define the momentum going here, P minus K. This one going in the same direction of the line will be K prime. But this is just, if I'm calling this guy K, right? This is just k plus q, right? So you see I have k rotating the clockwise direction here. So all momentum conservation is fine. And now I can write the Feynman rules for this loop, right? And this is just minus I e to the cube, integral in the loop momentum, d4k over 2 pi to the fourth, and then the loop itself, right? So I'll just go in this direction starting from this point, right? So I'll just call these, I have to associate Lorentz indexes to all those points. I start with gamma nu, then the propagator here is I chi prime slash plus m over chi prime square minus m square. Again, I'm suppressing the plus I epsilon just to keep our notation a little more clean, right? But a little cleaner. But keep in mind, if I need the I epsilon, I'll bring it back. Then I call this vertex gamma mu, right? The factors of charge are are already outside. Right? Now the propagator with k, it's just k slash plus m over k square minus m square. Then the last vertex there is gamma rho, right? And the photon propagator, which is minus I g, he's connecting these two vertices, so it's nu rho over k minus p square. And again, as I said at the start, right, these guys probably causing an infrared divergence when the momentum of the photon goes to zero. So in order to deal with that, for now, I'll just put an infrared regulator, which is a fake mass for the photon, right? We'll have control over this divergence later if I keep this parameter here and see what happens when it goes to zero. If the resulting expression diverges when this guy goes to zero, it means I have an infrared divergence, right? Now I can simplify this a little bit, right? I have 6 powers of I here, right? And so there's a minus is cube, right? Just repeat the integral. And I have these denominators here that I'll put all of them together. Let me rewrite. So now I write this k prime explicitly. It's k plus q square minus m square. This term. Now this one, just k square minus m square. And this one is k minus p square minus m gamma square. And the numerator is just these products of gamma matrices, and again I'm writing k prime explicitly, q slash plus m, this one gamma mu, this guy k slash plus m, and then this one, which I can contract with g nu rho here to get a nu right here, right? In principle, I can use some identities to bring these Dirac matrices together, right? But I don't want to use that right now because we know those relations change when I go away from 4 dimensions, right? And I will be using dimensional regularization. So for now, I want to keep these in this way so I don't lose epsilon factors that come from when I'm not exactly into 4 dimensions, right? So now I want to use Feynman parameterization for this expression. I'll call this guy A. This guy will be B. And I will have C here, right? Just to organize things. And I can rewrite the integral, right? Or at least the, better yet, this fraction just as an integral into 3 Feynman parameters, which I'll call x, y, and z. Then I have a delta of x plus y plus z minus 1. So the sum of these three guys is always 1. And I'll use the following choice. I'll put x multiplying a, y multiplying b, and z multiplying c, and all of that will be to the power 3 because I have 3 of these denominators. Right now I can simplify things a bit. Right, I'll need to expand this denominator and complete the squares. So I want xa plus yb plus zc, right, to be a complete square, and that I can get just by writing everything explicitly. I'll get a k square, right? So k is square is in every one of them, so it will be multiplied by x plus y plus z, which in the presence of this delta function will be always 1, right? And the rest of the expression is just right here. I'll be a little bit less explicit in the calculations now because we did these calculations again and again, right? And they are getting really long, but there's no new tricks, right? There's essentially the same kind of calculations we did before, but with more terms, right? Just more algebra. But conceptually, you know how to do these calculations if you have been following the course so far. So just have to see it and do them yourself. You see that there's really no new tricks going around here. It's just the same tricks to more complicated cases, right? And so I want to complete squares here. So I really have to look at the terms that are this term, right? I want to eliminate this linear term in k, right? And it is easy to see that I could write k mu. Let me use a different color, right? I could, this is the whole expression, just take these and do the full expansion. Now I can see that if I take a term which is k mu plus y q mu minus z p mu, and take the square of this, right? I'll get this k squared term, I'll get k this term here, and I'll get this one too, right? But I'll get more stuff which I need to subtract. So this I have to subtract because I'll get an extra here and it's not present here, y square q square. Neither is z square p square, right? And neither is another cross term between these two guys, which is plus 2 y z q scalar p, right? So these three terms I need to subtract, but that expression is the same as the one here, right? And this is what I need to complete the square. So I just have to call this this momentum L mu and make a change of variables from K to L in the momentum integral, right? If I do that, I can rewrite this expression in terms of L, right? And that will be, also keep in mind, right? I'm always thinking that the momentum for the electrons is on shell. So P square is really M, M is always the mass of the electron. I'm calling the mass of the photon, this fictitious mass for the photon m gamma, right? And everywhere I see p square, I can replace that for m, right? And just with a little momentum conservation algebra, you see that this is also easy to calculate in terms of q. We did that before. This is q square over 2. Right? So there's, again, same tricks as before, right? And I can, by using those relations, I can simplify this complicated thing to this m gamma square plus y minus y square minus y z q square. So this is all the terms proportional to q square. And then I can group all the terms proportional to the mass square. That will be z minus z square minus x minus y m square. And then I can use, always using that x plus y plus z is 1, I can simplify these things a bit, right? And that leads to a much simpler expression, which is L square minus, and now I'll put this minus in front here because I want to call the resulting expression delta, as we did before, right? xy q square plus 1 minus z square m square. So, and that in order to get to that, I use that this guy here is just y x, right? And this guy is just minus z minus 1 square. All you have to do is substitute one of these guys by 1 minus the other two, and you can get to those expressions. Now, this thing here, I, as always, will call everyone in here I'll call delta square, right? The square is just symbol. I will never use this guy linearly, right? Never take the square root of this. But it's just to remember that this has, then delta has dimensions of momentum, right? And I will indicate a gamma here, as we did in the previous video, to remind me that I'm regularizing this in the infrared with a fictitious mass for the photon. If I take m gamma going to 0, then this guy just becomes delta square, which has this piece removed, right? And always remember, this is a function of also the momentum, this momentum of the photon. So now we need to go back to the numerator here, right? This numerator, and do the same substitution of k for L, right? And then do a bunch of algebra with these Dirac matrices to simplify my my numerator, right? I won't do that here. That's a lot of algebra. It's a fair amount of algebra. The important things to keep in mind, right, is a few tricks you can always use, right? The first one is to remember that this function is sandwiched between this u bar of p prime and this u of p. So if you get p prime slash to the left here or p slash to the right, you can substitute this for the mass using Dirac equation. Also, another thing that you can use here is the Gordon identity. Eventually you get a p prime plus p, right? And that can be substituted by a part that has only gamma mu and another one that has the structure of F2, right? Because we want to write this in terms of something times gamma mu and another something times this structure, because that will allow me to see the correction to the form factors, right? And finally, if you do this algebra, you have to do it carefully, because when you use relations like this one, you always want to do that in d dimensions, right? You get three terms instead of just two, one proportional to gamma mu and another one sigma mu nu q nu, right? You get three terms, but the third one integrates to zero. You can see that using parity arguments, right? So you can find this calculation done somewhat with some level of detail in Schwartz book, and also in some old lecture notes of mine from 2016. I'll link both into the video description. Right? The important point is when you do that, you can rewrite these loops in this form, right? Where delta f1 is this loop correction that is proportional to gamma mu, so it's the correction to the f1 form factor, and delta f2 is the part of this loop that is proportional to this structure, and that's the correction to the f2 form factor, which was 0 at 3 level. Remember, this guy was present at 3 level, but this one was 0. Now, delta f2 is actually finite in the UV. You can do some power counting here and see. So we don't need to regularize it in the ultraviolet. The infrared regularization is still here, right? But we don't need a UV regularization. And F1 isn't like that, right? F1 is actually divergent in the ultraviolet. And that's why we did dimensional regularization here. So you can see all the factors of D that appear, right? These ones are the ones you know. And the ones in here all came from commuting Dirac matrices with those P slashes and K slashes and L slashes that we had in the numerator, right? So that's basically the expressions you get. And now let's first focus on this finite part that comes from delta of f2. Let me copy this one. And keep in mind that we expected delta f2 to be finite because it's connected directly, right, to the anomalous magnetic moment of the electron, right? Now we'll be able to calculate that explicitly, right? That's what we're looking for here, right? So the next step in this calculation is to really rotate to the Euclidean. So I can put a Euclidean here that brings minus I out here, right? In fact, an I outside, but then there's another minus that comes from this denominator here because this guy will become minus LE squared, but then I can bring a sign out of this cube here, and that will become a minus I squared out here, right? And which then it's just 1. And this integral we have done before, right? A few videos ago, we calculated this. This is just a finite, and it's equal to 1 over 32 pi square delta gamma square. Of course, in this case, there's also the z times 1 minus z in the numerator, but that's not part of the integral, really. Okay? So using that, I can rewrite this guy in this way. Right? This is just, we can cancel a lot of factors here. I'll exchange this e square for 4 pi. Right? I'll take this e squared and exchange for 4 pi alpha, right? So that becomes m squared alpha over pi, right? This absorbs a lot of the powers of 2 here and pi, right? And you're left with the integral over the Feynman parameters and this, right, of z 1 minus z. And then, of course, I have to write delta explicitly because delta depends on the Feynman parameters, right? So it's z m gamma square minus x y q square plus 1 minus z square m square, right? This is just delta that I wrote explicitly. All the powers of 32 pi square is already included here, right? Now, remember, this is the expression of delta F2 of Q square, right? Which is the first one loop contribution to F2. Remember, F2 of Q square was 0 at tree level, and this is the first contribution, right? And I could, in principle, integrate these, but I'm not that interested in the result, right? What I'm really interested is the calculation of these for Q square equals 0, because that's the definition of the contribution to the anomalous magnetic moment, right? So I want to calculate this guy, right? So I can repeat this expression here, right? And put Q squared to 0. This goes away. Also, you can see that there's no infrared singularities here by taking this guy to 0. If you cannot see it straight away, it's fine, as if there was a problem, the resulting integral would diverge. Let me put everything together here. You get a really simple expression for this integral in z, right? Now m squared goes away. Between this term and this one, there's a power of 1 over z that goes away too here in the denominator together with this, right? So you just get the integral of z over 1 minus z, right? That's not hard to do. First, you just use the Dirac delta, and that gives us an integral of alpha over pi, integral from 0 to 1 dz. I did the integral in x first, right? That means that y, because of this delta, I want to keep the integral where I hit that delta, otherwise the result is 0, right? So y needs to go from 0 to 1 minus z, right? dy of z 1 minus z, okay? That's the integral I want to do. And that's just, you can integrate that really quickly, and that's just 1/2. So this is alpha over 2 pi. Which, if I plug, and that's very important. Suppose I want to use the number we know by heart for alpha, which is 1 over 137, right? Which is an approximate value for alpha. Then this value, I just divide that by 2 pi, will be 0.00111617, right? And I put in a lot of numbers here, but I don't know, I didn't say yet how precise we know the number of alpha. So just as a comparison, right? Just as a comparison, as we have seen, right? F2 of 0, right, is g minus 2 over 2, right? Where g is the magnetic moment of the electron, right? And then when you subtract 2, it becomes the anomalous, right? How much it deviates from 2, right? The most precise measurement of this listed in the particle data group website, and just for future reference, we're recording this video in 2023, right? The most precise experimental measurement for this, let's call this g minus 2 over 2 experimental, is this number. Now, this is scary in terms of how precise the measurement is, right? 596 5218073, and the uncertainty is on these last two numbers, 28. So plus or minus 28 here, right? Which is scary precise measurements, right? And you can compare those two, right? But in fact, and you'll find, wow, this is fine, right? But actually, that's not how it works, right? For a long while, this was the most precise measurement in QED, right? And that meant that actually this was used to calculate alpha, and not the other way around, right? You use that measurement in an expression, which is not this one, right? But instead, the order alpha 4 correction to delta F2, right? And that was used to fix the value of alpha. Right? Nowadays, we have better measurements of alpha, and then you can use the value you know alpha from other measurements to predict what will be the anomalous magnetic moment for the electron, right? In fact, nowadays, again, this is about 2 sigma away, right? If you take the better number for alpha and see how much G minus 2 will be, that's about 2 sigma away for the electron from what you expected, which is fine, right? 2 sigma is expected in some measurements, especially measurements this precise. But it is important to understand what's the game here, right? Because alpha is not directly observable, right? The actual test you do of QED at higher loop orders is to make many QED observations which are independent amongst themselves, right? Calculate the theoretical prediction for each of those, and in each of those measurements, you get a different value for alpha, right? Because they are independent measurements. And then if all those alphas agree, they are essentially the same alpha, that means that QED is working, right? Essentially what you do is many independent measurements of alpha, and you're trying to change this one variable. Of course, there's a few other variables like the mass of the electron and other free parameters here and there, but essentially you're trying to fit everything. If you marginalize over the other parameters, you're trying to fit all these independent measurements with just one free parameter, which is alpha. So let's take a look on how that fit looks nowadays. And here it goes, right? So what you're seeing here is 1 over alpha, right? Minus 137 and something, right? Time 10 to the 6, right? So what you're seeing here is deviations in one part into 10 to the 6 from 137, right? And you can see that roughly all these values of alpha agree, right? 1 over alpha in this case, right? Remember that you never directly measured alpha, so the theoretical uncertainties are also included here, because you usually have to go to many loop calculation of QED to actually be able to compare with experiments at this level of the precision, right? So not all loop orders are calculated exactly, so you have approximations on the theoretical side too, but still really impressive on how the agreement is, right? Especially you can see that in this plot on the box here, which is a blow up of these points, right? You can see that it's going even to the 10, one part, I mean 0.1 10 to the 6 here, right? And this is from the paper that does this very last measurement here, the most precise ever. And the precision is so impressive that they couldn't even resist including how good the precision is in the title of the paper, right? I'm pretty sure, not 100% sure, but I'm pretty sure this is the most precise measurement of anything ever, right? And the best agreement between theory and experiment in all sciences, right? This is the most successful science ever, most successful theory to ever be proposed, right? Is really QED, right? So that's the status, and I think it's a pretty interesting calculation, because now you can see how these loop effects are not only physical but important, right? It would be way off by many sigma, considering how small a sigma here is here, if you didn't include loop effects and decide that the alpha is just 1 over 127, or better yet, that the anomalous magnetic moment is the magnetic moment is just 2. There's no anomalous magnetic moment, right? That would be completely excluded by now with this precision of measurement. Now, for the sake of completeness, let's go and calculate the F1 part, right? The delta F1, the first loop correction to F1, and see what we get, right? So first notice that there's a part here proportional to L square, and another part that has no powers in the numerator, right? Just by, again, power counting here, you can see that this part, just like the F2 form factor part, is finite. So really the only part that diverges is this one that has L square over this denominator. Right? Let's calculate this part first. So I'm interested in taking this term. Let me copy the part that interests me. We'll calculate both, but let's start with this one, which is this whole common part multiplied by this thing here. I want to know how this integral behaves. Again, I have to go to the Euclidean, which means a sign coming from here, right? An factor of I coming from here, but there's also another sign from this guy, right? So the two signs cancel each other, and just have an I that comes out here and gets these minus and these I. So I'm left with just 2e squared times this whole thing, right? Now I want to calculate these integrals, right? We have formulas for these that we have derived in previous videos, right? So we can use those to rewrite these, to do the integral in the Euclidean L here. Let me just copy the parts I'm not integrating yet, which is the Feynman parameter part, right? I'm doing this integral together with the factors here. This is not integrated either. Let me just remove the colors, right? And everything else is just the result of the integral of L squared over this denominator with that, which is, I'll write all in yellow here, is 4 pi to the power minus d over 2, gamma of 2 minus d over 2 over gamma of 3, gamma of 1 plus d over 2, gamma of d over 2, and gamma square, delta square of gamma to the power 2 minus d over 2. If you don't remember this formula, go back a few videos and you'll find it. Right? So now this guy, I can use recursion relation for gammas to write this guy as d over 2 gamma of d of 2, and then the gamma cancels, right? And you get just d over 2. All of these is equal to d over 2, right? Which gives me a cancellation between this d and this one. This goes away, right? This is just 2 factorial, which is another power of half. I have a power of half here. A power of half there is just 1/4, right? So that allows me to rewrite this as 2e squared. I'm bringing this guy all the way next to the other things that depend on d, because then I have to expand near d equal 4, right? Z, repeat this delta, right? And then I'm just grouping all these guys together, right? Again, I'll put it in yellow, so mu 4 minus d, which is epsilon, right? 2 minus d square over 4. This 4 is just this times this, right? 4 pi d over 2, gamma of 2 minus d over 2 over this delta right there. Let me see if I can fit it down here. Now, you have to do a series expansion in epsilon, right? Which is, I can define an epsilon as 4 minus d. So this guy goes to 0 as d approaches 4, right? And I can do a series expansion. We did that again. This is another trick, which is, I mean, not a trick, but more like a method, right? That is getting old at this point. And that gives me just, let me name this guy just the integral of that complicated expression with the L squared part, right? Over L plus delta cubed, right? Just to give a name to this part, right? This is just 2e squared. When I do this expansion, as usual, you get a power of 16 pi squared out here, right? This is just repeated over because I'm not integrating on this part so far, right? And then this becomes the usual expression, which is 2 over epsilon minus 2 plus the log of mu tilde square over delta gamma square, which is very familiar from many similar calculations we did. And here, as you know, is the same definition I used before, right? Mu tilde is square is just 4 pi mu square exponential of minus the Euler Mascheroni constant, right? I'm including all these logs of 4 pi and this constant together with the mu, because this is all just a number and an arbitrary number that shouldn't appear in my observables anyway, right? So this is the divergent part of f1, right? So it's the integral of this part right here. Now I want to do this other integral. Let me copy everything and then I'll get rid of the L squared part. So this is one of the things I'm interested in. Let me put a box around it, right? The other one, which I'll call similarly to this, I'll just call this the 1 part. Right? Instead of L squared, I just have a constant here in the numerator, right? For this guy, I can straight away, right, just have to erase this part, right? This is what I'm interested in. But since this is finite in the UV, I can actually take d equal 4, right? Exactly equal 4, so I can get rid of the dimensional regularization I did before, right? And that means this is just a 2 right here. This is just 4, right? And that's the integral I want to do, right? Let me group, just tidy up things a little bit. Right? This is what I want to calculate. This guy goes away. And let's do that. So I can rewrite this part as minus 2, 1 minus x, 1 minus y. Just have to substitute z for 1 minus x minus y. I can always use this to simplify terms. Similarly here in fact I just have to expand. This is just minus 2 plus 8z minus 2z squared. Again, I'm not doing the calculations in too much detail because it's just algebra. And I have to go to the Euclidean here, right? If I go to the Euclidean in this part, I get a sign, right? And there's an I coming from here. So that's a total of minus I here, right? Which will cancel this I here and give me another sign, right? And now, in fact, I'll bring a sign out from these two parts here. Right? So that's 2e squared. In principle, I have a minus here, but you see I'll compensate inside the integrals. I have the integral on the Feynman parameters. Let me copy that here. Just manage my screen space here. And the integral, right? Once you did all these simplifications, the integral in D4LE is again the same one we did for F2, right? It's just the integral of these 1 over LE squared delta squared to the cube, right? So again, is that expression I wrote up there is 1 over 32 pi square delta. We did this integral way back in the scalar case. Right? It's the same integral that keeps showing again and again. And everything in here is just 2. 1 minus x, 1 minus y. You see that sign, it's compensated for out there. And this is just 2 times 1 minus 4z minus z squared m squared. Right, so this expression right there, some cancellations here. I can take this 2 and this 2 and make that a 16 here, because I want to group that with the 16 pi squared from this other part, right? And now I can put these two expressions together, right? I can just add them up, right? Let me write these here. Right? Once I add those two, I have delta F1 of Q squared, right? This is 2e squared over 16 pi squared. That's a common factor for both of them. You can see here, right? And of course, the integral in the parameter in the Feynman parameters is also common. And then I just have to add these with the part that is up there. Let me put a bracket like this, right? There I have the divergent part, the 2 over epsilon part, minus 2, plus the log of mu tilde square over delta gamma square. So just the thing I have in yellow here, right? And then I have, let me put it here, 1 over delta square times this thing. Close this bracket and then close this one, right? There you go. And I fixed a Q square that I was missing here and a sign here through the magic of video editing, right? So now we have this expression for delta F1, right? And if you remember, the normalization conditions, renormalization conditions for F1 demanded that F1 calculated at q square equals 0 should be 0, right? This comes straight from the renormalization condition for gamma, for the gamma 3 function of QED, right? Which I demanded that at this point, q square equals 0 should be just minus IE gamma mu, right? There's a mu index here, right? And same here. So F1, which is the part proportional to gamma, should be 1 at this point. If we go back to our diagrams, let me go all the way back to the top, right? You see that this is the full thing, right? And this is contributing actually at 3 level, minus IE gamma mu, right? So this contributes to the 1 part, right? If F1 is of q squared calculated at 0 is 1 plus delta F1 of 0, right? This is contributing to the 1. And then that means that these two parts, right, since F1 calculated at this point should be just 1, these other two parts, this one plus delta 1, this should be 0, right? So this is the condition that allows me to get the counter term from delta F1. So let's go back down there. And write that since that sum should be 0, that one the counter term should be minus delta of F1 calculated at q square equals 0, right? Now I can copy this expression here. There's this minus, which I'll put here, right? And now I have to set q squared to 0 everywhere here. So the first term that goes away is this, because there's a q square here, right? Also, delta is q square dependent, right? If I take q square to 0, delta gamma square loses the q square part, right? We can indicate it like that, right? And becomes just z m gamma square plus 1 minus z square m square, right? So I can use that here. Z m gamma square plus 1 minus z square m square, right? And also here, and this is what we want to calculate, right? Again, this integral is the kind of integral we have been asking Mathematica to do for us. I won't show the program, but it's actually doable, right? And then at the end, you have to expand this expression for small m gamma to take the leading terms as you go near the infrared pole, right? Since you already have the leading term as you go to the ultraviolet pole, right? And that means that this guy will become, now I can rewrite this guy right here as alpha over 4 pi, right? So you get a alpha over 2 pi right here. So delta 1 will be minus alpha over 2 pi times. The integral of this part is really easy, right? It's just, again, that factor of 1/2 that comes when you integrate over all the Feynman parameters. So this is just 1 over epsilon minus 1. And of course, the integral of the rest of this is more complicated, but still doable, right? And in the limit that you take, let me put like that, this comes from this part. And the rest, when you take the limit of small m gamma, right? This is, again, very similar to some expressions we obtained last video. It's just m gamma square over m square plus half of mu to the square over m square, right? Which is, right, exactly equal to the delta 2 we calculated before, right? As expected by the Ward-Takahashi identities in the same limit, right? Still expanding for small m gamma, but actually you don't have to do this integral. You can show that the integral before integrating the Feynman parameters is the same you had there, but you have to do some integration by parts to show that explicitly, right? So again, this is kind of a victory again for our confidence in the Ward-Takahashi identities, and shows that the symmetry works. And also this leaves us with this very explicit expression that has the infrared divergence and the UV divergence, which will be useful for us on the next video, when we finally discuss the infrared divergences of QED a little bit. I mean, I won't go too deep into that, but we'll at least understand where they are coming from. So that's it for this video. See you on the next one.